Thank you, everyone. As one of the 3 co-founders of PingCAP, I feel honored that PingCAP was once again invited to Percona Live. Last year, our CEO, Max Liu, have introduced TiDB and TiKV to the public. He mainly focused on how we build TiDB and has formulated a future plan of our project. This time, I will draw a detailed picture of the TiDB and help you understand how it works. And first of all, I'd like to introduce myself. My name is Edward, an infrastructure engineer and the CTO of PingCAP. Up to now, I have worked on 3 open source projects. Codis, a proxy-based Redis cluster solution, which is very popular in China. TiDB and TiKV, a SQL database that is our topic today. All of them are open source. It is many people benefit from them, especially in China. And I prefer languages such as Golang, Python, and Rust. Yeah. By the way, we are using Golang and Rust in our project. TiDB is written in Go. TiKV is written in Rust. And first of all, I want to ask a question. Yeah. What do you do when your RDBMS is becoming the bottleneck of your application? Maybe most of you have the experienced the following situation. In the old days, all you can do is either to refactor your application or use something like MySQL proxy or database middleware. But once you decide to use the sharding solution, it is a one-way path. You will never get rid of the sharding key and say goodbye to complex query. You cannot join. You cannot do the cross-shard transaction. So how to scale your relational database is really a big pain point of the entire industry, I think. And there comes TiDB. When we are designing TiDB, we want to achieve the following goals. One, make the sharding and the data movement transparent to users so that the developers can focus on application development. 2, 100% OLTP. You can do transaction, and 80% of OLAP. You can do some complex join or something like that and analyze workload. TiDB aims to be the hybrid database that supports both OLTP and OLAP. It is flexible because TiDB supports transaction, as I mentioned before, and we have our own full-feature distributed SQL engine, including parser, optimizer, and query executor. We build it from ground up. And TiDB has to be compatible with MySQL protocol. We implementing the MySQL grammar and the MySQL network protocol. In this way, our users can reuse many MySQL tools and greatly reduce the migration cost. You can use MySQL dump, MyLoader, MyDumper, yeah, something like that. And it is 24/7 availability, even in the case of data center outage. And thanks to the Raft consensus algorithm, TiDB can ensure the data consistency and availability all the time, mostly. And of course, it is open source. Yeah, fully open source. Apache 2.0. Yeah. This is the agenda of today's talk. First section, I will talk about the technical overview of TiDB and TiKV project, including the storage layer, a brief walk through our distributed SQL engine, and some tools for the community user to migrate from MySQL to TiDB or vice versa. Secondly, I will introduce some real-world case and some benchmarks. We got several users in China which have already used TiDB cluster in production for over 3 months. And in the end, I will do a quick demo of setting up the TiDB cluster and have some query on it. Well, let's see the TiDB architecture. In this diagram, there are three components: the SQL layer, which is TiDB server, and the distributed storage layer, which is TiKV. It's a key value database, and the placement driver, aka PD here. These three components communicate with each other through gRPC. And TiDB server is stateless. It doesn't store any data, and it is for computing only, just like Google F1. And anybody knows Google F1? Yeah. Oh, well. It translates users' SQL statement and generate the SQL plan, query plan, which present as the RPC calls to the TiKV layer. TiKV layer is the distributed key value database inspired by Google Spanner, acting as the underlying storage layer of TiDB, and it is a place where the data is actually stored. This layer uses Raft consensus algorithm to replicate data, not using multiplexers. We use Raft and guarantee the data safety. And the TiKV also implements distributed computing mechanism so that the SQL layer would be able to do something like predicate pushdown or distributed join or aggregator pushdown. And the placement driver is the managing components that the entire cluster and it stores the metadata, handles the timestamp allocation request for the ACID transaction, just like TrueTime for Google Spanner. But we don't have the hardware. Yeah, it is a timestamp allocator in software. And what's more, it is controlling the data movement for dynamic workload balance and failover. Yeah. So let's dive into the storage stack of TiKV. As I mentioned earlier, TiKV is the underlying storage layer where data is actually stored. More specifically, data is stored in RocksDB locally, which is the bottom layer of the TiKV stack. As you can see from this diagram, on top of RocksDB, we build the Raft layer. So what is Raft? Raft is a consensus algorithm. I think it equals to the multiplexers in fault tolerance and performance and correctness. Yeah, it has several key features such as leader election and the auto failover and membership changes. And Raft ensures that the data is safely replicated. And we have exposed the raw key value API at this layer. We have the raw key value API. If you want the scalable, high performance, highly available key value database and don't care about something like cross-row transaction or SQL, you can use the raw API here. You can use TiKV as a standalone key value database, kind of jumping replacement for HBase or something like that with high performance and lower latency. The middle layer is MVCC, multi-version concurrency control. The top two layers are transaction and the gRPC API. The API here is the transactional key value API, just like Spanner exposes the transactional key value API here. And the TiKV is written in Rust programming language. And the reason is that the storage layer is performance critical, and the stability is, of course, the first-class citizen. We only got C and C++ in the past, but right now we have Rust. Rust is great for infrastructure, system software, like database operating system, without any extra cost for GC and runtime. And it is designed for the high performance, the software. Another great thing is that Rust do a lot of works in preventing the memory leaks and data race. That means a lot of us. Yeah. Now we know that the actual data is stored in RocksDB, but how exactly the data organized inside the RocksDB instance? The answer is the region. Region is a set of continuous key value pairs in byte order. Let's take a look at the diagram here. The data is split into a set of continuous key value pairs, which we name them from A to Z. Region 1 stored A to Z, region 2 F to J, K to O, etc. Notice that the region is the logical concept. All the regions in same physical nodes shares the same RocksDB instance. In each RocksDB instance, I just mentioned before, there are several regions, and each region is replicated to another instance by Raft. The replica of the same region, for example, region 4, it is called the make a Raft group. The metadata of the Raft group is stored in placement driver, a PD. Yeah, of course, the placement driver is a cluster too. Replicate the metadata by Raft. Yeah, in this component. In TiDB, we adopt a multi-raft model. What is multi-raft? It is a way to split and merge region dynamically, and of course, safely. We name this approach safe split and merge. For example, region 1 from A to E is safely split into region 1.1, A to C, and D to E. We need to guarantee that no data is lost during the split. This explains how one region is split, but how about its replica on another nodes? Let's go to next few slides. This is the initial state of region 1. You can see that there is a Raft group with 3 TiKV nodes. Region 1 on TiKV1 is the leader, and the other 2 replicas are followers. However, there comes a situation that there are too much data in region 1. It needs to be split. The default size of the region is 64 megabytes. The split is initial by the leader, which means region 1 is split into region 1.1 and 1.2. Firstly, in the leader, as you can see from diagram, but not available for the query because the replicas are not split yet. When the split log is written to the WAL in the leader, the split log is replicated by Raft and sent to the followers. Then the followers apply the split log just like the normal Raft log. So the split log is just like normal write log replicated by Raft. And finally, once the split log is committed, all the replica in Raft group are safely split into 2 regions on each TiKV node. There's no data loss in the process. The correctness of the split procedure is ensured by Raft. Yeah, the whole database, the correctness is ensured by Raft. It built on top of Raft. Yeah.
So during the split, you said that there's no query can happen for the data set?
Pardon?
No, during
The split, okay.
and before it's commit, and you said there's no query?
No query, but it is not visible for the user. It's just the Raft is kind of 2-phrase commit, just like that. Just write the log, but not commit.
So after you commit, and before everything is replicated to the followers,
yeah.
There will be new update coming in, and how do you
because the Raft thread is a single thread. We have a lock on that split procedure and the read and write. So it is kind of atomic operation in each.
Before everything being replicated
Yeah. Now we have talked about the split. Let's see how TiKV scales out. Our project is as scalable as NoSQL system, which means that you can easily increase the capacity or balance the workload by just adding more machines. In this diagram, we have 4 physical nodes named A, B, C, and D, and we have 3 regions: region 1, 2, 3. We see there are 3 regions in node A. Let's say that node A encountered a capacity problem. Maybe the disk is almost full. To balance the data, we add a new node, node E. The first step is transfer the leadership from the replica of region A to node A to the replica on node B. Step 2, TiKV as a replica of region 1 to node E. Therefore, the region 1 have 4 replicas temporary. And the final step, TiKV removes the replica of region 1 from node A. Now the data is balanced and the cluster scale out from 4 nodes to 5 nodes. In the process of scale out, the data movement will be occur in different regions. So the result of the scheduling is that the number of regions is as equal as possible in every physical nodes. That's how TiKV scales out. Yeah, every region is 64 megabytes data blocks. Our transaction model is inspired by Google Percolator. It's mainly a decentralized two-phase commit protocol with some practical optimizations. This model relies on the timestamp allocator. We don't use TrueTime or HLC. So we use a timestamp allocator to assign increasing timestamp for each transaction. Hi. TiKV employs optimistic transaction model, and it only logs data in the final step of two-phase commit, which means it's the time that client call commit this function. Then they run the two-phase commit. In order to deal with the log problem, we when reading and writing data in two-phase commit stage, TiKV as a simple scheduler layer in the storage node to queue locally before returning to client for retry. If the transaction is conflict, we don't return the error to the client. We retry in the storage layer. And the default isolation level of TiKV is repeatable read, aka snapshot isolation, and it exposes the lock API. So when it's used to implementing the SSI, the serializable snapshot isolation level, such as select for update statement in MySQL. And we take the performance of TiDB very seriously. TiDB has a full-featured SQL layer for some operations. For example, select, count, star. There is no need for TiDB to get data from row to row and then count. The quicker way is that TiDB push down these operations to the corresponding TiKV nodes. The TiKV nodes do the computing, and then TiDB aggregate the final results to the client. Yeah. So we have a distributed join, and we build a distributed cost-based optimizer. Cost-based optimizer, aka CBO, is to optimize the plan by calculating the query cost. This optimizer is very complex. There are 2 key problems. One is how to get the true distribution information of the data. Another one is that how to estimate the cost of the certain query based on the the distribution information. Yeah. And this diagram shows that the architecture of the SQL layer. Let's take a look and see how the process works. And the client sends the SQL to the protocol layer, this protocol layer. Within the life cycle of the connection, we need to maintain the connection context and then get the structured request, which will be further processed in the SQL core layers, right? Core layers. Inside the SQL core layer, we need to maintain the sanction context, which includes all the related information, such as the variable of the sanction scope. Meanwhile, the sanction context is also the entrance of the SQL layer. After the SQL statement enters the SQL layer, the parser passes the SQL statement into AST. AST, and then the next step is process the AST, including the validation, name resolution, type infer, privilege management, etc. And then the next layer is the optimizer. There are two optimizers, the logical optimizer and the physical optimizer. The first step is that logical optimization, which transfer each AST to the logical plan and optimize the SQL logic based on the logical plan. The physical optimizer makes the physical plan, which then execute by the distributed executor. Here, the optimizer just like the boss who made the plan, the executor like the employees that execute the plan and perform the RPC calls. And there are also some crucial components like privilege management, schema manager, DDL worker. By the way, we implement a non-blocking DDL on our database. Yeah, by the paper, asynchronous schema change in Google F1. And GC worker, background job worker, just name a few. Now, we have talked about the process. Let's see an example how to show how this going on behind the query. Assume that we have a schema in with two fields and had the index. Now we need to run the following query. Select count C1 from T where C1 greater than 10 and C2 equals to Percona. This is a very simple statement, and the logical plan is very simple too. But in a distributed database, it needs distributed computing in most cases. Let's see the next slide to show the statement is executed in TiDB. This is the physical plan of the SQL statement. The SQL layer and the storage layer work together. Some predicate and the aggregator is pushed down to TiKV, and then send the partial result back to the TiDB server for the final aggregation. And there are several advantages of in this approach. First, there are more nodes involved in the computing, and therefore the computing become faster because maybe the table is very big. The data is separate. In this is many TiKV nodes, and we push down the aggregator and computing locally. Expand. And TiDB supports explain statement. That is a powerful tool for tuning SQL. So let's run this explain on this query. Okay. Okay. It's a table scale. Oh. well, the output is the physical plan generated by TiDB in JSON, not just like the MySQL. So let's go back to the slides. Well, where's my slides? Okay. Okay. Well, where's my mouse? The time is run out. I will rush. TiDB supports join, and let's see what happens behind the join. We create two tables, left and right. Is a join where the ID equals right table's ID. For this query, optimizer may choose hash join. Because hash join perform well in processing the small and medium-sized data, we implemented the operator and optimized it in parallel data processing, make it streaming. To join the table mentioned in previous query, the TiDB reads the table in parallel. When reading the smaller table, TiDB start to build the hash table in memory. When reading the bigger table, the data is sent to several join worker. When the hash table is finished, and then start join in streaming and output the join the table. It is a hash join. TiDB SQL Layer currently supports three kinds of distributed join type. One is hash join, sort merge join, and when the optimizer thinks that even the smallest table is too large to fit in memory, and then there is a predicate contains indexed column, optimizer will choose the sort merge join. Another is index lookup join. To help user exploit the best part of TiDB, we have prepared the following tools: Syncer, TiDB binlog, and MyDumper and MyLoader. I will introduce them in the coming slides. It is open source too. First is Syncer. Syncer is a tool to synchronize data from MySQL in real time. Let's take a look at the following diagram. We have a MySQL master with binlog enable, and the Syncer acts as the fake slave. At every beginning, Syncer gets the position of the current binlog, and which is the initial synchronization position. When there's a new data is written into MySQL, Syncer obtains the binlog from master, synchronize the data to the save point in disk, and then apply the root filter and set the data to either MySQL or a TiDB cluster.
So is Syncer like that?
Yeah, binlog represent. Yeah. On the other hand, TiDB can output binlog too. We built the TiDB binlog toolset to make it possible for third-party application synchronize the data from TiDB cluster. And because TiDB server is distributed, you can use many TiDB servers in different physical nodes. And so the binlog pumper should be deployed in every TiDB server instance and send it to the component we call Sister. Sister will sort the transactions by transaction ID, aka the timestamp, the timestamp in short period of time, and output as the total buffer formatted the data or the MySQL binlog to the downstream application or another TiDB cluster. Yeah, or even you can pass the protobuf data and send it to the Kafka to synchronize to another system. Yeah. And for data migration, we don't have our own tool. We use MyDumper, MyLoader. It is I think it's maintained by Percona. It is for MySQL data backup and restore in parallel. It is MySQL. It's a tool for MySQL community. Because we speak MySQL community, so we use this tool. And you can use MyDumper to export data from MySQL, MySQL, and use MyLoader to import the data into TiDB. For the data migration. And some real-world use cases. Currently, we have about 20 customers are using TiDB in production. There are more than 100 POC users contacting us and trying the open source version. Let's take Mobike. It's a company as an example. Mobike is the world's largest station-free bike sharing platform, and it is kind of one of the most famous startups in China for recent years. It now has nearly 500 million orders and the workload is really heavy, and that is the single MySQL is almost impossible to maintain. But on the other hand, engineers in Mobike want to use MySQL grammar because their application is already depends on MySQL in early days, and they don't want to refactor their application because time is money for this startup, and TiDB saved their days. They use a 7 nodes TiDB cluster for their transactional production database for order, so store the order transactional data. And on the other hand, Mobike shift to TiDB and runs 10 nodes cluster for ad-hoc OLAP query. They use Syncer, just I mentioned before, to synchronize data from multiple MySQL instance to one offline TiDB cluster, so that the data analyst can run some ad hoc OLAP query on the TiDB cluster using MySQL grammar. Yeah.
Can I ask a question? You say 7-node TiDB cluster, so that obviously has 3 different nodes. How do you distribute how many TiDB layers do you have and how many TiKVs? All of those are in the cluster.
No, this TiKV 5 and the 2 is TiDB server. Yeah. And let's see, this graph is for the compression of the query. Sorry. This is compression query elapsed in TiDB and MySQL. As you can see, the ad hoc OLAP with 8 queries. The time that MySQL takes almost 4 or 5 times more than the 3 nodes TiDB. It is from our customer, the real world query case. And another customer is using TiDB as a dropping replacement for MySQL, MySQL for OLTP workload. You can see the graph. I think it's too small. This is dashboard of TiDB, and thank you, Grafana. The latency of the 80% query, the top line, is lower than 3 milliseconds. The average query latency is about 5 milliseconds, and it is quite stable. And this is the storage status of this cluster. You can see, oh well, it's too small. That it is 18 nodes cluster. 18 is TiDB nodes. Yeah. Well, we run the Sysbench. We have some Sysbench result for read and insert. And here's the detail of the system we are using. Just like it's a normal PC. For read, you can see the more nodes, the higher QPS, the lower latency. 3 node is 20,000, 40,000, and about 58,000. 3, 6, 9 nodes TiDB. This diagram of the read QPS shows that the same result. The read performance improves significantly as the number of the nodes grows. That's insert. Insert is because we have 3 replicas, 6,000, 10,000, 14,000. Well, yeah, for insert, it is the same story. Yeah, that's SQL at scale, our slogan. And the final section of my speech is our roadmap to the future. We are now working on TiSpark, a project integrate TiKV, which the key value data, the underlying storage layer, integrate with Spark SQL. You can use Spark SQL to do some heavy OLAP query, and you don't need to use the heavy ETL job to migrate the data to another data warehouse like Hive or something like that. You can use Spark SQL directly read data from the TiKV, and we implementing some Spark SQL operator in the TiKV nodes so that the Spark SQL could push down the query plan to, we expose the data locality to the Spark SQL so they can generate the right query plan for the TiKV. We will announce our job in July, yeah, in the Hadoop conference. And we are still improving the static collection framework and the CBO optimizer. It is a long-term job. Yeah. Another big thing is that the JSON type and the document store for TiDB is have already put on our agenda. So because the document store is introduced into MySQL in 5.7, we are going to implement the same interface with MySQL document store. And we are going to make TiDB integrate with Kubernetes. Then that makes it very easy to set up a large cluster. And I will do the quick demo using Kubernetes to set up a cluster. So demo time. Okay, we have times. Okay. I write a simple demo for the TiDB cluster. Now we create the cluster name test 4 1 TiDB, 1 PD, and 3 TiKV. Okay. It is creating. First, we create a PD instance. You can see through the Kubernetes dashboard. You can see the container is now creating the containers using Kubernetes. Yeah. Three nodes, a little slow because it is creating the containers. Wow, really slow.
Where can you run this?
My laptop, I use MiniCube. Yeah, MiniCube. Wow, my Kubernetes stocks. Yeah. Oh, maybe something wrong with this little cluster. Wow. Wow, really slow. Oh, maybe something wrong with my Kubernetes environment. Oh. This time, do you have some questions? Hi.
Hi. You had an example with account query. What happens if we add distinct to the account? How the plan changes? How you do distribute distinct?
Distinct. Yeah. Distinct is really hard to distinct. Distinct, we fetch the data and fetch the data. Yeah.
So what do you just fail to think or try to do something?
No, we don't have anything to do by using the distributed distinct. It is very hard problem. This problem we are working on, but if you want to do a distinct on really big table and you don't have the index, so that's we need have to we don't have any yeah. Yeah, we support this thing, but maybe you could OOM. We will build the hash table in the memory, but if the table is too large part.
The question, the algorithms you showed for join,
yeah,
looks like there is no fallback for the case when you join or not.
Yeah.
Primary key and both are large. Are there any options to do that, or just you fail to? If you join or non-primary key, both are large.
If you join two large table, non-keys, that the performance is not very well on this case. We will fetch all the data into one node. We don't have the
Assume it's like petabyte on tens of petabytes to dense So it's pretty large, and does it fit even on this possible or not?
I don't get your question. We will discuss offline, maybe. Yeah, okay. Any questions? Oh.
Short question. Where those large installations you are aware of? So it's have you ever seen like hundreds of nodes or thousands of nodes?
You means we have tested TiDB in 400 nodes cluster. Not in production, our test. The biggest cluster in production is about 13 nodes. That is 13. Yeah, 13 physical nodes. Yeah. Okay. The cluster is set up. This is the dashboard. Okay. Wow. My laptop is really slow. Wow. Okay, something wrong with my Kubernetes environment. Yeah, it set up a three nodes cluster. That wow, really slow. Yeah, we can use MySQL client to connect to the TiDB cluster and do some query. Oh, I think there's something wrong with my container. Yeah. Okay, do you guys have any questions? Hi.
So what's the conversion to Cockroach DB?
Oh.
Like same area, or are there integrated with one over the other?
Okay. I think Cockroach DB, we have the same goal, the open source implementation of Google Spanner, but we are compatible with MySQL. We use MySQL protocol, and another thing is that we use different transaction model. Our transaction model is based on the Google Percolator, but not the HLC or in the heavy OLTP scenario. I think our transaction model is better because we don't have much scenarios like the cross data center synchronization. I don't think it will work without hardware, the true-time hardware. So the transaction model is different. We work well in the same data centers, not cross data center. Another thing is that we can use TiKV standalone as a key value database. And the Cockroach DB is the SQL layer and the key value layer are in the same node, but we are separated. Yeah. That's it. Okay.
Just a question about locality. If you've got different tables which really have keys or indexes which are similar, or data which is similar, can you locate the similar tables with similar values together to enhance performance and things, or is that not something that's possible now?
Yeah. You can consider the TiKV is the ordered map. So the same table will have the same prefix. So the table, the data in the same table will almost in the same physical nodes or nearby. We we are not using the hash sharding. So I think it is, yeah. So we push down the aggregator to the regions that the same table in the same region. So it is not the performance is well in that scenario. Okay. Okay. So now that's it. Thank you. Yeah.